This is the lecture for Monday, March 23rd. Today we'll be continuing our discussion of many-body theory, and we'll focus on the topic density functional theory. So density functional theory is the idea that you can probe the structure of the nucleus by focusing on the densities of the protons and neutrons. So a lot of the foundations of density functional theory were developed for electronic structure, the wave function for electrons in a solid or in some complex molecule. And one of the founding papers on density functional theory is the so-called Hohenberg-Kohn theorem, which relates the densities, the single particle densities, let's say in the case of nuclear physics, the protons and neutron densities, to the potential that the potential that the protons and neutrons are feeling. So from the density profile, you can determine the potential, the average potential that the nucleons are feeling. And so the idea of density functional theory is to focus on these proton and neutron densities and try to get as much information out of them as possible. In fact, trying to make a connection between the energy and these single proton and neutron densities. Okay, so that's the idea of density functional theory. There is some function, or actually functionale, and the word functionale means it's a function of functions. Okay, so there's some energy E, that can be written in terms of integrals, products and integrals of the single particle densities, and you're trying to figure out what this looks like. But once you find what this looks like, you can then get a description of many nuclei all at once. Okay, so with nuclear density functional theory, you're working with two Fermi liquids, the protons and neutrons. And it's a self-bound system. The nuclei are compact objects, and you also have this superfluid property where there is pairing between opposite spins, up and down spins of the neutrons and the up and down spins of the protons. All right, so if you look at the mean field level, remember mean field means that you have a larger nucleus, and you think about pulling one nucleon out of that nucleus, and you ask that nucleon what is the average potential of all the other nucleons that is exerting a force on it. And so at that mean field level, you're talking about what are then the one-body densities that you get. So these mean field terms give you these one-body densities. But you may also then look at correlations where you have, for example, zero-range interactions, meaning point-like interactions. Right? In that case, you would then multiply these single particle densities together to get some local density approximation. But you might relax the zero-range condition, and then you would have not just products of densities, but you would have products of densities with perhaps spatial derivatives. So these are various terms that may appear in the density functional. So you might have something where you have the densities multiplied together at a point, or maybe you have terms where you have derivatives of the density multiplied at a point. So you then would, with the interactions, you might consider particle whole, or remember what a particle is. You have some Fermi level that's filled up to some, remember the Fermi level is the highest energy level that's filled, and everything below it is filled. And if you have a hole beneath, that's what's called a hole. If you have a particle, if you have excitation above, that's what's called a particle. And so you may then have some interaction that couples these particles and holes to each other, as well as you may have interactions between particles with other particles of opposite spin. These are what are called pairing channels. So anyways, with these density functional theory calculations, you try to come up with some energy density functional fit to some empirical data, and then you make predictions for what the various details of the structure of the nucleus looks like. So here are some densities for the protons and neutrons for tin 100, where you have an equal number of protons and neutrons. And then you have zinc 100, where there's a lot more neutrons than protons. You can see the neutron skin here for zinc, this extra skin that's forming. Okay, so we can talk about this nuclear density functional, energy density functional. You have terms like what's called the isoscalar term, which you have the summation of the neutron and the proton densities, and then you can also have what are called the isovector terms, which are the neutron minus the proton. So scalar means 0, vector means 1. So this is isospin 0 and isospin 1. You also have all sorts of other densities that you can talk about: the spin density, the current density, and so on. But anyways, the energy density functional is some integral over all of space of some h, giving you the density functional. And so you may have various terms like the kinetic energy term. You might have some particle hole density. You might have some particle density. All right, so you can have this. For example, you can try to determine this energy density functional from microscopic physics, from some ab initio calculations. But you might be more empirical as to where these terms come from. With most practitioners, there's on the order of maybe a dozen terms that you include in your energy density functional. Okay, you would do some expansion in the densities and the derivatives. Some terms would probe specific pieces of experimental data. There are some things that are poorly determined, like, for example, the pairing part of the density functional is difficult to pin down. In some cases, there's some symmetry arguments where you may be able to constrain your density functional a bit better. Now, then there's also so-called multi-reference density functional theory, where you make some complicated sort of combination of different shapes for your nucleus. Here are some results from some density functional theory calculations. Here are predictions for a given density functional of the experiment minus the theory energies as a function of the so this is all across the nuclear chart. Here's the number of neutrons, and you can see the average error is on the order of about 0.58 MeV, which is pretty good. The RMS error is how this is defined. And here is now some density functional theory calculations for the alpha separation energy. Here you can see the results as a function of neutron number. And this is by density functional theory. It's a class of density functionals called Skyrm density functionals, known as SLY4. And you can see the predictions in the lines doing a pretty good job in comparison with the dots, which are the experimental values. And clearly you can see there are predictions for cases where the data is not yet observed. So with density functional theory, which is a very efficient way of doing these calculations, you can essentially predict all across the nuclear chart. So here is the number of isotopes for a given atomic number, what's been observed, what EFRIB is predicted to see when it turns on after a year and a half or so. And here is, from density functional theory, the prediction of all the bound isotopes that are possible. And so with Skyrm density functional theory, this, as I mentioned, Skyrm density functionals is a class of density functionals. There's a prediction of about 7,000 bound isotopes. Now, you can use density functional theory for various other applications. So you can do, for example, time-dependent density functional theory. You can try to describe deformation, some collective behavior, some deformed behavior, collective motion of the particles. So here's an example of shape coexistence. Here is some various magnesium isotopes which are known to be deformed for the various 0 plus, 2 plus, second 0 plus, second 2 plus states. And you can see, remember, these deformation, these plots here that show you that, so this is an example of a spherical nucleus. Here's then a prolate deformed nucleus, all right, and you can see these various density functional calculations make predictions for the various deformations. Okay. You can also use density functional theory to describe the reactions. Here's sort of a sequence of events of calcium-48 about to collide with uranium-238. You can see there's a merger, and then you see there's then a fission process that occurs. Now, you can also do calculations of various cross-sections. So here's a fusion of calcium-48 with calcium-48, and you can see the density functional theory from time-dependent density functional theory, TDDFT, and it's doing pretty well in comparison with the experimental data shown with the dots. Now, you can also use density functional theory to describe the many-body physics of neutron stars. So here are some calculations of the various so-called, what are called nuclear pasta shapes you get as at different densities. So here are here's a density of 0.032 nucleons per cubic femtometer. So low densities, you have these more stringy-like structures. And then you have somewhat more complicated sort of ripples here at density 0.057, and use slightly higher densities. You get sort of these little bubbles are forming, some sort of hollows you can see in these structures. And this is supposed to correspond with what you see in the crust of a neutron star. So then this can be used to predict what happens then in neutron star mergers as being observed by LIGO. Okay, you can also do just the properties of the neutron star itself. And by the way, the properties of the neutron star are very much related to the properties of the neutron skin in lead-208. So here's just showing correlations between some properties of the neutron star radius at 1.4 solar masses. Okay. In the correlation, there's a nice correlation with the neutron skin of lead-208. So here's just a wrap-up of what we've been talking about with many-body theory. So there's this merger of high-performance computing and nuclear theory, where you have analytic theory, experiment, as well as supercomputing calculations that allow us to bring together theory, experiment, and computation. And let me just read this quotation. High-performance computing provides answers to questions that neither experiment nor analytic theory can address. Hence, it becomes the third leg supporting the field of nuclear physics from the National Academy Decadal Study Report. Okay, and in the future, there will be large multi-institutional efforts that involving strong coupling between physics, computer science, and applied math. So, in the time remaining, I'm going to talk a little bit about quantum chromodynamics. Here are little artistic renderings of nucleons with the various quarks inside of them. Okay, so here's a little bit of the history. So quantum chromodynamics, or QCD, is the theory that describes the action of the strong force. So quantum chromodynamics is a lot like quantum electrodynamics, which will actually be what we will talk about mostly for the remainder of this lecture. And this is the quantum field theory of the electromagnetic force. So quantum field theory is the marriage of quantum mechanics with relativistic dynamics. So relativity and quantum mechanics. So in QED, quantum electrodynamics, the electromagnetic interactions of charged particles are described through the the emission and absorption of massless photons. So we have, for example, we have electrons that are interacting with each other by exchanging a photon. Okay. So here's my gamma, my photon. It's a virtual photon being exchanged, and that's what produces the, let's say, the Coulomb repulsion between two electrons. By analogy with QED, quantum chromodynamics predicts the existence of gluons. So here we have electrons, now we have, let's say, quarks, and the idea is that with quarks it's kind of the same idea, but instead we have some other force-mediating particles, and these are what are called the gluons. Okay, and part of the beauty of this is that it's similar to QED, but it's different, and it looks structurally the same, but there's a slight difference which causes all the difference in the world in terms of the fact that the strong interactions are strong and they confine quarks, whereas the electromagnetic interactions are relatively mild or weak in strength, and they do not confine electrons. Okay, so there's this gluon that transmits the strong force. And carries what we call the color charge. Okay. Now this idea of a color charge, so the idea here is that the quarks have some color, just like the charged particles in electrodynamics can be positive or negative. The color charge turns out you can have three different colors: red, blue, and green is what we call them. This color charge was first proposed by Greenberg in 1964. This was actually to resolve what is called the spin statistics contradiction. So it was known that there were particles that look like maybe. So now we understand them to be having three quarks, right? Just imagine you have three quarks. They're all spin up, and they all have these same. They all occupy the same space, all right? Now, the Paul exclusion principle tells you that this can't happen. So this is kind of a totally confusing scenario, but there are hadrons that have this sort of structure to them. But the idea is that there's actually another quantum number that's actually the redness, blueness, or greenness of the quarks, and so these guys have one of each, but in some completely antisymmetric combination, meaning I can have red, blue, and green, but then I have minus the other ordering where I have blue, red, and green, minus the ordering where I have red, green, and blue, and then so on, where it's completely anti-symmetric, meaning that exchanging any two gives me a minus sign in the wave function. If I have that sort of a wave function, then I have the Fermi statistics for my quarks, which is exactly what is needed, and so that's the resolution. Now, there's other reasons to believe all of this, though. There's also the work of Nambu and Han that talked about a group what's called an octet of gluons. So these gluons themselves have color to them. They can be thought of as having a combination of, for example, red with an anti-blue. So there's some color with an anti-color for the gluons, and so turns out to be 8 such combinations, and that's why it's called an octet. Then there's also in 1972 Gell-Mann and Fritsch. They made the term, or they coined the term quantum chromodynamics as the gauge theory of the strong interactions, and they use this theory of Yang and Mills that was mostly just a mathematical paper, a more mathematically motivated paper that described sort of the analog, the generalization of quantum electrodynamics for the case where there is a more complicated gauge symmetry involved. I know that's something that I'm not going to be able to explain in detail here, but the idea is that in quantum electrodynamics, this photon allows you to have a gauge symmetry where you do some sort of multiply. Imagine you have two different points in space, and you have some wave function of some particle, And you can imagine multiplying by some phase here, that e to the I theta at some point here x, and then you might multiply by a different phase, e to the I theta at x prime. And in order for that to be a symmetry of Lagrangian, it turns out that you need to have a photon to make this work. So this is what's called a gauge symmetry. All right? And similarly, you can do something like this for quantum chromodynamics, but in this case, you're not just multiplying by phase here or here. What you're doing is you're actually doing a matrix rotation, okay? And this turns out to be an SU3 matrix rotation that you do on the quarks. And the 3 actually corresponds to the fact that there are 3 colors. Okay, we'll talk more about this later. But in the beginning of the course, we talked about SU3. We touched on it because, because actually I wanted you to be able to understand this when we finally reach this point where we talked about quantum chromodynamics. Okay, but coming back here, there was this theory of Yang and Mills to describe this sort of gauge theory with these matrix rotations. And so this was now finally being used to describe quantum chromodynamics. Here's one case where the mathematical structure was written down without knowing the application, and then finally the physics application came in later. This may be actually a pretty good place to stop. We're going to pick up next time talking about the quantum electrodynamics Lagrangian, the Lagrangian that describes the interactions of quantum electrodynamics, in particular the electron and the photons.